For Module 19D, we're going to kind of delve back into what we covered in first semester and see how we can apply it to second semester. You should be able to determine the standard entropy of reaction from the standard molar entropies of products and reactants. This is very similar to what we did with enthalpy in first semester, using Hess's law. Use your equation delta G equals delta H minus T delta S to be able to calculate your free energy, Gibbs free energy or G, of a reaction and determine the temperature at which a non-spontaneous reaction will become spontaneous. Be able to determine the standard free energy or Gibbs free energy of a reaction using either your delta G equals delta H minus T delta S equation or the standard free energies of formation. So, a review on delta H. Remember that delta H is your enthalpy change, but we often call this the heat of the reaction because delta H is equal to Q at constant pressure. Q being heat, so delta H is equal to the heat of the reaction under constant pressure conditions. Delta H is not actually heat, but you can think of it like being like heat. Delta H, even though it's not actually heat, is heat flow under constant conditions, or under constant pressure conditions. So if delta H of a reaction is negative, what does that mean? If delta H of a reaction is positive, what does that mean? Well, delta H for reaction being negative, we call that exothermic. That means if we make our little person, our little system, that heat has left. The system has lost heat to the surroundings. If delta H for reaction is positive, we call this endothermic. In this case, heat has been added to the system from the surroundings. Delta H, when we write that little superscript, like the little, I call it delta H naught, this means standard enthalpy change. And specifically, that means that if you have gases, every gas is at 1 atmosphere of pressure. And every solution concentration is 1 molar. If you see the delta H naught with a sub F after it, that little F means formation. This is your standard enthalpy of formation. Or heat of formation. And delta H naught sub F is just a specific shorthand for a particular thermochemical equation, specifically for a formation reaction. Hopefully that is at least somewhere in the back of your brain as a review from first semester. As a reminder, a formation reaction is when we form 1 mole of a substance from its elements in their most stable form. So 1 mole of the product that we want. And formation reactions are the only time that you're going to find fractions in balanced equations. If we have a polyatomic or a diatomic, polyatomic meaning like S8, P4, that kind of thing, or a diatomic, we may have fractions in a formation reaction because we can only form 1 mole of the product. So let's look at this example. Calculations involving thermodynamic data at 298.15 K. We've got a table here of delta H formation, delta S formation, delta G formation values. We've got this, it says delta H formation, CO2 is negative 393.5 kilojoules per mole. What does this really mean? Well, writing this, the short piece here, is shorthand for writing the following. Carbon graphite plus O2 gas yields CO2 gas, and the delta H naught of reaction here is negative 393.5 kilojoules. What this is telling me, this in a much simplified form compared to below, is that in a thermochemical equation, we write kilojoules, not kilojoules per mole, because the coefficients in the equation stand for the number of moles in the reaction. By writing delta H sub F, I am defining this as a formation reaction, meaning that I know I'm only forming 1 mole of CO2 for this reaction. So then, by writing it delta H of reaction, I'm stating, again, this is forming 1 mole. What if I wrote delta H formation of H2O as negative 285.8 kilojoules per mole? Well, that's shorthand for writing H2 gas plus 1/2 O2 gas yields H2O. Depending on the temperature, this could be gas or liquid. But in this case, the formation, it is, this value here is for the formation of liquid. Delta H reaction, negative 285.8 kilojoules. This illustrates that sometimes fractional coefficients are required. As we said, formation reaction is the formation of 1 mole of your product. So in this case, I need H2O. I need 1 water in my final product, so I need 1/2 mole of O2. So sometimes fractional coefficients are required. If I said delta H formation of O2 is equal to 0 kilojoules per mole, this is like writing O2 gas going to O2 gas, delta H reaction equals 0. Basically, nothing happened. So delta G not a formation, delta H not a formation are always 0 for any neutral element in its most stable form because nothing happens. key there also being in its most stable form. Why do I say in its most stable form? Because we have 7 elements that exist as diatomics. Those are the most stable form of those elements. Carbon, graphite is the most stable form of carbon. You've got sulfur that likes S8, etc. We've got elements that iron just likes to be Fe solid, aluminum, Al solid. It's whatever's in its most stable form because it doesn't have to do anything to get there. It's already there. And delta H formation of C6H12O6 equals negative 1274 kilojoules per mole. This is shorthand for writing 6 moles of carbon graphite plus 6 moles of H2 gas plus 3 moles of O2 gas, yielding C6H12O6 solid, and delta H of reaction here, negative 1274 kilojoules. This illustrates that formation reactions, which is what this is, the formation of 1 mole of your desired product, delta H formation, are often hypothetical or idealized. This reaction isn't going to actually happen this way. 6 moles of carbon does not react with 6 moles of H2 to form 3 moles of O2. However, the delta H formation value for this compound is still a true value. And because I keep forgetting to take it out of the slides, I should note that this is delta H of formation, delta G of formation, but this should just be S, not here. It should not be the change in S. It should just be S here. I know, I apologize for that. I keep forgetting to take out the little delta sign in front of that S. So how does this deal with Hess's law? Well, like I said, Hess's law comes back. Hess's law states that the total enthalpy change, delta H, for a process is the same, regardless of whether the reaction occurs in one step or many steps. This is because of the first law of thermodynamics. Energy cannot be created nor destroyed. Stuff doesn't appear just out of thin air. There's no free lunch. It had to come from somewhere and has to go somewhere. We can rewrite this by saying delta H reaction is equal to the sum of the number of moles of product times the delta H formation for each product minus the sum of the number of moles of the reactant times the delta H of formation for that specific reactant, all of those summed together. This is like saying A plus B goes to C plus D. Delta H reaction here would be equal to the sum of the delta H formation of A plus the delta H formation of B minus the sum of the delta H of C plus delta H formation of D. So I remember this as products minus reactants. But you have to remember that you're multiplying up with the number of moles of each species as well. But the same principle applies to entropy and Gibbs free energy. We can follow the same process. We can also, another application of Hess's law is when we had given reactions and we were trying to find a target reaction, we can manipulate those reactions to find our target reaction. We can do that as well for delta S and delta G because they're all state functions. So let's work a couple examples. Determine delta H, delta G, and delta S for the combustion of 1 mole of glucose, C6H12O6. Okay, combusting glucose. C6H12O6, solid, plus O2 gas, gives me CO2 gas, plus H2O liquid. Need to balance this thing. So 6 carbon, 12 hydrogen, 12 hydrogen. Now I have 12 plus 6, I have 18 oxygen. There's 6 here. So I need another 12 oxygen, so I need to put a 6 in front of this oxygen here. Make sure that's balanced. 6 carbon, 6 carbon, yes. 12 hydrogen, yes. 6 plus 12 oxygen, 6 plus 12 oxygen, yes. So in order to, I'm going to have to write these out and then erase them, but because I did not leave enough room on the slide to do this. And we'd have to look up these values, but I'm going to give you the values. So for, let's see, for C6H12O6, the value we saw on the previous slide was 1274.0 kilojoules per mole. And if you want to scroll back, you can find them in the back slides as well. And this is for delta H. For O2, it's its most stable state. That is 0 kilojoules per mole. For CO2, negative 393.5 kilojoules per mole. And for H2, we used that one in an example very recently as well. Negative 285.8 kilojoules per mole. So the way I'm going to do this, I'm going to do the products minus reactants thing. So it's going to be the sum of the number of moles, so 6 moles CO2 times delta H formation of CO2 plus 6 moles of water times delta H formation of water. So that's my products minus my reactants. 1 mole C6H12O6 times delta H formation C6H12O6 plus 6 moles of O2 times delta H formation of O2. Let's go ahead and plug in the numbers we have. So delta H for this reaction, 6 moles CO2 times negative 393.5 kilojoules per mole. That cancels out my moles for me. Plus 6 moles H2O times negative 285.8 kilojoules per mole. That cancels out my moles here. Is the sum of that. Let's see, where am I? Minus 1 mole C6H12O6 times negative 1274.0 kilojoules per mole. Cancels moles there. Plus 6 moles of O2 times 0.00 kilojoules per mole. Cancels moles there. Add this all up, and I get, no space left, delta H of reaction equal to negative 2,879.6 kilojoules. Oh, I just wrote the wrong value too. I'm sorry. I was looking on the wrong part of my notes instead of trying to recalculate it. Negative 2,801.8 kilojoules. That is the delta H value. I was writing down delta G. So delta H, negative 2,801.8 kilojoules. But I can do the same exact thing with delta G and delta S. I can follow the same pattern. So pause this if you need to write all this down, because I need to erase all this. And I am going to cheat and erase parts. So delta G and delta S can be calculated the exact same way. We can say delta E of formation, or delta G of formation for each species, and plug in their values. Now, the delta G values are the following respectively. Let's see. 910.0 kilojoules per mole for C6H12O6. 0 kilojoules per mole for O2 because it's its most stable state. 394.4 kilojoules per mole for CO2. And negative 237.2 kilojoules per mole for water. Plug in all of our values. So 6 moles of CO2 times 394.4 kilojoules per mole. 6 moles of H2O times negative 237.2 kilojoules per mole. 1 mole of C6H12O6 times 910.0 kilojoules per mole. And 0.00 kilojoules per mole for O2. Notice again that all of your moles cancel out here. And your final delta G value here is negative 2,879.6 kilojoules. And because we haven't been glutton for punishment enough, we're going to do the same exact process all over again for delta S. Let's write our delta S values up here, though. Delta S for C6H12O6, 212.1. This is joules per mole K. Notice these units are different. They have temperature involved, and they're in joules, not kilojoules. For O2, it is 205.0 joules per mole K. Remember the definition of entropy. It's 0 at absolute 0. We are not at absolute 0, so all species will have values. Whether they be a pure element in its most stable form or not, they will have a value. CO2, 213.6 joules per mole K. And H2O, 69.9 joules per mole K. You're going to follow that exact same process again, everything we just wrote out. And this will be S standard instead of delta S. I always write the delta symbol because it's such a habit, but it should just be S naught. This is change in S here, though, for the reaction overall, because we are calculating the overall change in the reaction. So, for CO2, 213.6 joules per mole K. Moles canceling out. For H2O, 69.9 joules per mole K. With moles canceling out. For C6H12O6, 212.1 joules per mole K. With moles canceling out. And for O2, 205.0 joules per mole K. With moles canceling out. And my delta S of my overall reaction here equal to negative 356.1 joules per Kelvin because moles have canceled out. Hopefully that was all painful. Well, that's not the hopeful part. Hopefully that was all review. It was painful, but hopefully it was all review and everything makes sense and you guys remember how to do that. You can do that for delta H as well as delta G and delta S. Again, you can also use the equations to manipulate the equations. I call it putting together a puzzle where I give you the given equations and a target equation and you manipulate those given equations to determine the target equation. But there's one more question we have not answered on this slide yet. How could you determine delta G naught reaction for this reaction using a different approach? The other approach would be using delta G equals delta H minus T delta S. Now, we would have still had to calculate delta H and delta S for the reactions to be able to do this. One note, I do not know what I was adding up earlier, but please note that I actually wrote down the wrong value for this one. I don't know what I was looking at. This should be 258.9 joules per Kelvin. Sorry, I'm really not sure where I pulled that other number from. But this should be 258.9 joules per Kelvin here. So, for delta S, I can actually use the delta H and delta S values I calculated previously to calculate delta G. So delta G is equal to negative 2,801.8 kilojoules minus the temperature. What temperature do I use? When you see that little knot symbol, that means 25 degrees C or 298.15 K. So minus 298.15 K times my S, but this is in kilojoules. I need this in kilojoules as well. 0.2589 kilojoules per Kelvin. Note that your kelvins cancel out here. Now I've got kilojoules minus kilojoules. And let's see where my sig figs are actually at, because I'm not sure on that one. 298.15 times 0.2589. Okay, this gives me 77.19 kilojoules. If I'm adding it to this, then I can keep one decimal place. So 2,801.8 minus 77.19. And let me see, here I get an answer of negative 2,878.99, which rounds up negative 2,879.0 kilojoules, which is off just by rounding error at that point. So same answer. So you can get delta G either direction. Make sure when you plug in this calculator, you remember that there is a negative sign out here. Okay, so make sure you remember those negative signs because that can affect your answers as well. You can see we can calculate delta G either way. So there are a few other things you need to understand about thermodynamic tables. First, again, as I've mentioned, the table does not give delta S naught, even though I tend to write it that way because I forget. It actually gives you S naught, or entropy, the absolute entropy. That's due to the second law of thermodynamics, how we can actually measure the exact entropy of the system. There's no subscript F in the entropy column, even though I tend to forget that too. We only got that subscript F for delta H and delta G. And that's because the subscript F refers to a formation reaction. When I write S naught, this is the absolute entropy. It's completely independent of any reactions. And again, I know I mentioned this in the previous slide, but be careful of units. Delta H of your reaction and delta G of the reaction are in kilojoules per mole. S, or your entropy, is in joules per mole K. I don't care what you do with your units, but you have to be consistent. So we're looking at delta G equals delta H minus T delta S. This is in kilojoules per mole. This is kilojoules per mole. And this is joules per mole K. This is in Kelvin. Just be consistent with your units, please. Be consistent, meaning convert one unit convert to just 1 unit, okay? And compare the magnitudes. S naught is usually much smaller than delta H of reaction and delta G of the reaction. Delta H and delta G are often similar, meaning they're in the same ballpark. Delta S is usually very, very small comparative. And if you head on into chemistry, you will find that in P-Chem, we use this equation. Delta G is delta H minus T delta S. In organic, they say that delta G is approximately delta H. This makes us happy. This makes us sad. It's not incorrect to say that when it comes to organic systems. It's not correct, though, either. The reason we can say that delta G is approximately delta H is because delta S is such a small, magnitude compared to the others. So it really is delta G and delta H very comparable to one another. But they're not the same thing. In P-Chem, we take it very seriously to make sure that they're actually the same thing. Delta G naught and delta G. What is the difference between these? So it's important to note that delta H, delta S, and delta G are all dependent upon your reaction conditions. For example, changing the pressure will change the entropy. If I have a system that I compress, so I've got gases here. I compress this. This has a higher entropy because the particles have more places they can be. This has a lower entropy because there's just less places for the molecules to be. Since conditions must be specified, we often use standard state conditions. The standard state conditions are as follows. For solids and liquids, this is them in their pure form. For gases, each gas is at a partial pressure of 1 atmosphere. If you have something dissolved, a solution, each solute, remember the solute is what is dissolved in the solvent. Each solute has a concentration of 1 molar, or 1.00 moles per liter is the other way to write that. Temperature must be specified, but if the temperature is not explicitly stated, you assume that T is equal to 298.15 K. And delta G naught is called your standard free energy change. Delta G is the free energy change that occurs when the reactants in their standard states are completely converted to products in their standard state.